Hi, we are discussing the harmonic oscillator problem. In the last class, we obtained the eigenvalue spectrum and also the eigenkets for the harmonic oscillator Hamiltonian. We used the Dirac's operator method to obtain the eigenvalue spectrum and also the eigenkets. In this class, we shall continue our discussion of the harmonic oscillator, and we shall mainly illustrate some of the things that we have learned so far. We will be calculating the matrix elements for the operators x and p. We shall obtain the energy eigenfunctions in position space. We will calculate the expectation values of x, p, x square, p square, etc. We shall also illustrate the generalized uncertainty relation. For this, we will be calculating the products of position and momentum uncertainties in the ground state and also in excited states. Before going into all those, let's revise what we already learned in the previous class. We started with the harmonic oscillator Hamiltonian, which is h is equal to p square divided by 2m plus half m omega square x square. And in an attempt to factorize this Hamiltonian, we defined two operators a and a dagger. From the commutation relation, from the fundamental commutation relation between x and p, we found the commutation relation between these two operators a and a dagger, and the commutation relations gave us commutator of a with a dagger is equal to 1. We defined the number operator n is equal to a dagger a. We showed that the Hamiltonian operator can be written in terms of these new operators a and a dagger as h bar omega is equal to a dagger a plus half. Writing a dagger a as n, the number operator, the Hamiltonian becomes h bar omega n plus half. Clearly, the Hamiltonian commutes with the number operator, which also means that n and h have common eigenkets denoted as ket n. So the eigenvalue equations are n acting on ket n gives you n multiplied by ket n, where n, the small n, are the eigenvalues of the number operator. And you can obtain the eigenvalue equation for the Hamiltonian also. H acting on ket n becomes h bar omega n plus half multiplying ket n. So the energy eigenvalues are En is equal to h bar omega multiplying n plus half. So we label the energy eigenvalues using the eigenvalue of the number operator. We discussed the physical significance of operators A and A dagger. A is called the annihilation operator or the lowering operator, and this name is justified because A acting on ket n is an energy eigenstate with energy h bar omega less than the state ket n. Okay, that's what we have written here. H acting on A ket n is equal to h bar omega n plus half minus h bar omega multiplying A ket n. What we have here is the eigenvalue corresponding to the state n. So what we see is that the eigenvalue corresponding to the state A ket n is the eigenvalue corresponding to the state ket n minus a unit of energy. Okay, so it lowers the operator A lowers the energy of the state denoted by ket n. This is the reason why it's called the annihilation operator or the lowering operator. We also called A dagger the creation operator or the raising operator because we saw that A dagger acting on ket n is a state with energy h bar omega greater than the state ket n. That's what this equation means. H acting on A dagger n is h bar omega n plus half, which is the eigenvalue corresponding to the state ket n, plus h bar omega multiplying A dagger ket n. So A dagger ket n has a higher energy compared to the state ket n, and the energy is higher by 1 unit of energy, h bar omega. Okay. From the normalization requirement of energy eigenkets, we found that A acting on ket n is equal to square root of n multiplying ket n minus 1, and A dagger acting on ket n is equal to square root of n plus 1 multiplying ket n plus 1. Here, the states ket n plus 1, ket n minus 1, etc. are the normalized eigenkets of the number operator and the Hamiltonian. Then we saw something very important regarding the nature of this n, because n itself can be written as the norm of a ket, and the norm of a ket cannot be negative, which means that n has to be non-negative. And the fact that n is non-negative also implies that n is an integer. So n has to be a non-negative integer. This can be seen easily because suppose n is non-negative but a non-integer. If n is a non-integer, say like 1.5, alright, if n is a non-integer, then we can apply the annihilation operator successively to it and reach a state with a lower value for n. So applying the annihilation operator to this will give 1.5, square root of 1.5 multiplied by get 1.5 minus 1 according to this relation, which is get 0.5. Okay. Now if we apply the annihilation operator once more to it, a square acting on get 1.5, this would be square root of 1.5 multiplied by square root of 0.5 multiplying the get 0.5 minus 1, which is minus 0.5. Okay, so if we start with a non-integer value for n, by successively applying the annihilation operator to it, we can reach a state with a negative value for n, but n cannot be negative. However, if we start with an integer value for n, right, then applying the annihilation operator successively to it will reach or will take us to a state corresponding to n equal to 0. For example, suppose we start with n equal to 1, or let's say n equal to 2. All right, and applying the annihilation operator once to this state, according to this relation, this becomes square root of 2 multiplied by get 1. We can apply the annihilation operator again. A square acting on get 2 would be equal to square root of 2 square root of 1 multiplying get 0. So we have reached a state corresponding to n equal to 0. Now if we apply the annihilation operator again to this state, okay, what we get is square root of 2 square root of 1 multiplying square root of 0 multiplying ket minus 1. But this is 0 multiplying ket minus 1, which means that this is a null ket. This entire thing is 0. So if we start with an integer value for n, by applying the annihilation operator successively, you cannot go beyond get 0 because the annihilation operator acting on get 0 gives 0. It returns a null ket, which means that n cannot be lower than 0 or n cannot be negative. So the lowest possible value for n is 0. Okay. And this state also corresponds to the lowest energy because we had the energy eigenvalues En is equal to n plus half h bar omega. If n equal to 0, we have E0 is equal to half h bar omega, which is called the ground state energy, and the state gets 0 itself is called the ground state. Okay. The ground state is the state with the lowest value for energy. And here, remarkably, the lowest value for energy that a harmonic oscillator can take is not 0, it is half h bar omega. Now we have the ground state denoted as ket 0. We can obtain all other energy eigenkets by starting with ket 0 and applying the creation operator successively to it. Okay? And the normalized eigenkets corresponding to higher energies can be obtained as ket n is equal to a dagger raised to n, which means that a dagger is applied n times, okay, divided by square root of n factorial acting on ket 0. In this way, we can construct simultaneous eigenkets of n and h with energy eigenvalues En is equal to n plus half h bar omega, where n can take values 0, 1, 2, 3, etc. And that's where we concluded the last class. Let's now move on to the next part where we shall calculate certain matrix elements and wave functions. Just for quick reference, we have A is equal to square root of m omega divided by 2h bar x plus ip by m omega, where x and p are the position and momentum operators respectively. And A dagger is equal to square root of m omega divided by 2h bar x minus ip divided by m omega. It's going to be useful to write x and p in terms of a and a dagger. For this, first you add a and a dagger. We see that the second term here cancels and we are left with square root of m omega divided by 2h bar multiplying 2x, which is equal to square root of 2m omega divided by h bar multiplying x. Okay, from here we find that x can be written as square root of h bar divided by 2m omega a plus a dagger. So that's the position operator in terms of the creation operator and the annihilation operator. Similarly, you can solve for p. You start with a minus a dagger, which is equal to square root of m omega divided by 2h bar twice IP divided by m omega. Right? These two terms get added up. You can solve this expression for P to get P is equal to I multiplied by square root of h bar m omega divided by 2 multiplying minus A plus A dagger. So now we have the position operator and the momentum operator written in terms of A and A dagger. Memorizing these expressions is going to be very useful when you solve problems. So I have written them again here. X equal to square root of h bar divided by 2 m omega A plus A dagger, and P is equal to I multiplying square root of m h bar omega divided by 2 multiplying minus A plus A dagger. In the first chapter, we saw that operators can be represented by matrices. As an example, let's find the matrix elements of X and P operators in the basis formed by the energy eigenkets. Since X and P can be written in terms of A and A dagger, let's start by finding the matrix elements for A and A dagger. The matrix element for operator A, let's denote it as A subscript n prime n. This is defined as bra n prime A ket n. Now we can use the relation A acting on ket n is equal to square root of n multiplying ket n minus 1. So this becomes bra n prime square root of n multiplying ket n minus 1. Square root of n is a number, it can be pulled out. So this becomes square root of n multiplying bra n prime ket n minus 1. Now we said that the energy eigenkets form an orthonormal basis, which means that this inner product is going to be 0 unless n prime is equal to n minus 1. So we may write this as square root of n delta n prime comma n minus 1. For example, if you want to find the 1 1 matrix element of operator A, let's call it A11, this would be equal to, according to this relation, okay, this would be equal to square root of 1 multiplying delta n prime here is 1, but n minus 1 is 0. Okay, so this is 0. All right, which means that A11 is equal to 0. Whereas if you want to calculate the matrix element A12, here n prime is 1, n is 2. You see that n prime is equal to n minus 1. So according to this relation, this matrix element is equal to square root of n, which here is square root of 2, multiplying delta n prime is 1, n minus 1 is 2 minus 1, which is also 1. So A12 will be square root of 2. In the same way, using the relation A dagger acting on ket n is equal to square root of n plus 1 multiplying ket n plus 1, you can find the matrix element for operator A dagger, which is given as square root of n plus 1 delta n prime n plus 1. Okay. We can also derive the matrix elements for X and P. To find the matrix element of X, bra n prime X ket n, we can write X in terms of A and A dagger according to this relation that we have already seen. So we write X equal to square root of h bar divided by 2 m omega A plus A dagger. The square root of h bar divided by 2 m omega can be pulled out because it's a number, and then we have bra n prime A plus A dagger ket n. These are the matrix elements of A and A dagger, which we already found. So we can write using them bra n prime X ket n is equal to square root of h bar divided by 2 m omega square root of n delta n prime n minus 1, which are the matrix elements for operator A, and square root of n plus 1 delta n prime n plus 1, which are the matrix elements for operator A dagger. Okay. In the same way, we can find the matrix elements for operator P also. The n prime n matrix element of P is given as bra n prime P ket n. We substitute P in terms of A and A dagger using this relation, and we have bra n prime I multiplying square root of h bar m omega divided by 2 minus A plus A dagger ket n. Again, this I square root of h bar m omega divided by 2 can be pulled out, and we are left with bra n prime minus A plus A dagger ket n. We have already found the matrix elements for A and A dagger. So this is simply I square root of h bar m omega divided by 2 multiplying minus square root of n delta n prime n minus 1. There's a minus here because there's a minus here. and then the matrix element for operator A dagger, which is square root of n plus 1 delta n prime n plus 1. As an example, let's find the matrix element, the 1, 2 matrix element of operator P. So according to this relation, this would be I square root of h bar m omega divided by 2. Right here we have got, this is n prime and this is n. So we have got minus square root of 2 delta n prime n minus 1. You see that n prime is indeed n minus 1. So this is 1 plus square root of n plus 1, which is square root of 3. But here we have delta n prime n plus 1. And n plus 1 is not equal to n prime, which means that this term is 0. Okay, so the 1, 2 matrix element of operator P in this basis, in the basis formed by the energy eigenkets, is equal to minus I root 2 square root of h bar m omega divided by 2. Or this can be written as minus I square root of h bar m omega. In this way, we can find all the matrix elements of operator P that we need. I hope that the calculations are clear. We have calculated the matrix elements for x and p in the basis formed by the eigenkets of the number operator. We can call this the n representation, and it's clear that in this representation neither x nor p is diagonal. You can go back to our expression for the matrix elements for x and p and see that these are not diagonal. Clearly there are non-diagonal elements which are non-zero. In the example that we saw that P12 is not equal to 0, which means that P is not a diagonal matrix in this representation. There is no surprise in this because X and P do not commute with the number operator. Okay, so you can easily show that the commutator of X with N is not equal to 0. Similarly, the commutator of P with N is also not equal to 0. It's easy to check these commutation relations. You just write x and p in terms of a and a dagger. And the number operator itself is a dagger multiplied by a. And you will see that these commutators are actually non-zero. This means that x and n cannot be simultaneously diagonalized. P and n also cannot be simultaneously diagonalized. In fact, x and p cannot be simultaneously diagonalized because the commutator of x and p is equal to 0. So there is no representation in which these operators can be simultaneously diagonalized. Okay. We can use the operator method also to obtain the energy eigenfunctions in position space. That is, we can find the position representation of the energy eigenkets. We know that a state ket alpha is represented in the position basis by bra x prime ket alpha, which is called the wave function. Here, ket x prime are the position eigenvectors obeying the eigenvalue equation. X acting on ket x prime is equal to x prime multiplying ket x prime. Remember that x here is the position operator, whereas x prime here is the eigenvalue. Let's now start with the ground state. The ground state is defined by A acting on ket 0 is equal to 0. This relation says that this particular ket, A acting on ket 0, is a null ket. Okay. The corresponding expression in the position basis would be bra x prime A acting on ket 0 is equal to 0. Now we can use the expression for the annihilation operator. A is equal to square root of m omega divided by 2 h bar x plus ip divided by m omega. Substituting this expression for the annihilation operator in here, the equation becomes bra x prime A ket 0 is equal to square root of m omega divided by 2 h bar bra x prime x plus ip divided by m omega acting on ket 0 is equal to 0. Let's now recall the position representation of position and momentum operators. We had seen that if ket alpha is represented by bra x prime ket alpha, then the position operator acting on ket alpha is represented by x prime multiplying this wave function, x prime multiplying bra x prime ket alpha. In other words, the wave function representing this state, bra x prime x ket alpha, which is the wave function representing the state x acting on ket alpha. Okay, this is equal to x prime bra x prime ket alpha. Similarly, if we have a state ket alpha being represented in the position space as bra x prime ket alpha, then P acting on ket alpha is represented by minus IH bar d by dx prime of this wave function, d by dx prime of bra x prime ket alpha, which means that the position representation of the ket P acting on ket alpha, which is bra x prime P ket alpha. This is called the position representation of the ket P acting on ket alpha. Okay, this is equal to minus IH bar d by dx prime of bra x prime ket alpha. That is, the wave function representing P acting on ket alpha is obtained from the wave function representing ket alpha by acting minus IH bar d by dx prime on it. These are things we have discussed in detail in the first chapter. Using this, we can write the wave function representing x acting on ket 0. Right? So this is a state. The wave function representing this state is bra x prime x acting on ket 0. Now, according to this relation, alright, this is equal to x prime multiplying bra x prime ket 0, or this is equal to x prime multiplying the wave function representing ket 0. Okay. Similarly, bra x prime ip divided by m omega acting on ket 0 can be written as I divided by m omega multiplied by bra x prime p acting on ket 0. And we know that the wave function representing P acting on ket 0, that is bra x prime P acting on ket 0, can be obtained from the wave function representing ket 0, which is bra x prime ket 0, by operating minus IH bar d by dx prime on it. Okay. So bra x prime IP divided by m omega ket 0 becomes h bar divided by m omega. Alright, there's an h bar here and m omega here, d by dx prime of the wave function representing ket 0. Okay, I hope this is clear. In this expression that we just obtained, h bar divided by m omega appearing here has the units of length squared or distance squared. I leave it as an exercise for you to check that this indeed has the units of length squared. So we can define a quantity x0, which is equal to square root of h bar divided by m omega with dimensions of length. Now if you look at this, this quantity x0 is constructed out of the parameters relevant to the oscillator, the mass and its angular frequency. It also involves this quantity h bar, which is relevant to quantum mechanics. So we can say that x0 sets the length scale for the quantum mechanical oscillator. This means that the displacements associated with the quantum mechanical oscillator are expected to be around this value x0. That's what we mean when we say that x0 sets the length scale for the quantum mechanical oscillator. It gives us an idea of the typical displacements associated with the quantum mechanical oscillator. Okay. We have bra x prime ip divided by m omega acting on ket 0 is equal to h bar divided by m omega d by dx prime bra x prime ket 0. Okay, and we defined this h bar divided by m omega as x0 squared. So this can now be written as bra x prime ip divided by m omega ket 0 is equal to x0 squared d by dx prime of bra x prime ket 0. And previously we had bra x prime x ket 0 is equal to x prime multiplying bra x prime ket 0. Now let's put all this in this equation. This is the equation that we started with. Bra x prime a acting on ket 0 is equal to square root of m omega divided by 2 h bar bra x prime x plus ip divided by m omega ket 0 is equal to 0. Now since square root of m omega divided by 2 h bar is not 0, we must have bra x prime x plus ip divided by m omega acting on ket 0 is equal to 0. We can split this bra x prime x acting on 0 plus bra x prime ip divided by m omega acting on 0 is equal to 0. Now we make use of these results. Okay, bra x prime x acting on ket 0 is equal to x prime multiplying bra x prime ket 0. So this term becomes x prime multiplying bra x prime ket 0, and this term is x0 squared. Okay, from here this term is x0 squared d by dx prime of bra x prime ket 0 is equal to 0. Or we can write this bra x prime kets 0 as a common term outside, and we get x prime plus x0 squared d by dx prime of bra x prime kets 0 is equal to 0. Okay. What we are trying to find is the ground state energy eigenfunction in the position basis. What we have here is the differential equation satisfied by the ground state energy eigenfunction. So all we need to do now is to solve this differential equation. Now this is a first order differential equation and it can be solved easily. We can rearrange the terms in this equation and write it as d by dx prime of bra x prime ket 0 is equal to minus x prime divided by x0 square bra x prime ket 0. Here we have the derivative of the function, and on the right side we get back the same function multiplied by some other function of x prime. You might have easily guessed the solution already, because we know that the exponential function satisfies this property. So we can guess that the solution is of the form a exponential and some function of x prime. Okay. We can find f of x prime by demanding that the derivative of f of x prime gives minus x prime divided by x0 squared. That would be one way to obtain the solution, or we could solve this directly. So this equation can now be written as d of bra x prime ket 0 by bra x prime ket 0 is equal to, so we bring this thing to the left side, all right, and the dx prime to the right side, and we can write this as d of bra x prime ket 0 by bra x prime ket 0 is equal to minus x prime divided by x0 squared multiplied by dx prime. Now it's easy to integrate on both sides, because what we have here on the left side is of the form dx by x, and the integral of dx by x is log of x. So integrating on both sides, we have log of bra x prime ket 0, and on the right side also the integration is simple because these are constants. Minus 1 by x0 square is a constant, and we are left with integral x prime dx prime. So the right hand side is minus 1 by x0 squared integral x prime dx prime, which is minus 1 divided by x0 square x prime square divided by 2 plus a constant. Okay, so we can write this as log of bra x prime ket 0 is equal to minus 1 divided by x0 squared x prime square divided by 2 plus a constant. Okay, now we can take the exponential on both sides, and since the exponential is the inverse function of the log, on the left hand side we get bra x prime ket 0 is equal to, and on the right we get exponential. We can write this as minus x prime squared divided by 2x0 squared, and there is also this term exponential of c. And this exponential of c is a constant, we can write it as a. So the solution has the form bra x prime ket 0 is equal to a exponential minus x prime squared divided by 2x0 squared. Okay. We now have the ground state energy eigenfunction. There is still an undetermined constant in here, and it can be determined by demanding the normalization condition. A wave function is said to be normalized if it satisfies integral minus infinity to infinity psi star of x psi of x dx is equal to 1, or integral minus infinity to infinity modulus psi of x squared dx is equal to 1. So the requirement that this wave function is normalized becomes modulus a squared integral minus infinity to infinity exponential minus x prime divided by x0 squared has to be equal to 1. Here we have a Gaussian integration of the form integral minus infinity to infinity exponential of minus ax squared dx, with a is equal to 1 divided by x0 squared. We have already discussed this integral when we talked about Gaussian wave packets. Over there, using gamma functions, we showed that this integral has a value square root of pi divided by a. So using this formula, the normalization condition now becomes modulus of a squared square root of pi by a. Square root of pi by a is square root of pi divided by 1 by x0 square. Okay, which is x0 multiplied by square root of pi. So the normalization condition now becomes modulus of a square x0 square root of pi is equal to 1, or modulus of a squared is equal to 1 divided by x0 square root of pi. From here we see that the wave function would be normalized if a is equal to 1 divided by x0 raised to 1 by 2 pi raised to 1 by 4. Okay, this is the normalization constant. We can now substitute a is equal to 1 divided by square root of x0 pi raised to 1 by 4 into this equation to get the normalized ground state wave function. So the normalized ground state wave function is now bra x prime ket 0 is equal to 1 divided by pi raised to 1 by 4 square root of x0 exponential minus half x prime divided by x0 squared. Let's now obtain the position space wave function representing the first excited state. The first excited state is ket1 and the position space wave function representing this state is bra x prime ket1. So we just need to evaluate bra x prime ket1. Okay, and ket1 itself can be written in terms of the ground state ket0. We can make use of the relation, the general relation ket n is equal to a dagger raised to n divided by square root of n factorial acting on ket0. So using this, ket1 is a dagger raised to 1 divided by square root of 1 factorial acting on ket0. So if we make this substitution here, the first excited state wave function becomes bra x prime a dagger divided by square root of 1 factorial acting on ket0. We can now substitute for a dagger because we know that a dagger is equal to square root of m omega divided by 2 h bar x minus I p divided by m omega. Now the square root of m omega divided by 2 h bar can be pulled out and bra x prime ket 1 becomes, or the first excited state wave function becomes 1 divided by square root of 1 factorial square root of m omega divided by 2 h bar and bra x prime x minus ip divided by m omega gets 0. Okay. Now let's look at this term. Well, let's look at this term. Let's evaluate this term. Bra x prime x minus ip divided by m omega gets 0. Okay, this can be written as bra x prime x gets 0 minus I divided by m omega bra x prime p gets 0. Okay, now we can make use of this. These things we have seen before. Bra x prime x ket 0 is equal to x prime multiplying bra x prime ket 0 and bra x prime p ket 0 is minus ih bar d by dx prime acting on bra x prime ket 0. Okay, so this term is written as x prime multiplying bra x prime ket 0. That's what we have here. All right. And here we substitute minus ih bar d by dx prime of bra x prime ket 0 from here. Okay, and it becomes minus I divided by m omega, which is already there. The rest of it is minus ih bar d by dx prime bra x prime ket 0. Okay. Now this I here and minus I multiply to give 1. And we have an h bar divided by m omega here. All right, and we already had defined x0 is equal to square root of h bar divided by m omega, which means that h bar divided by m omega that's appearing here can be written as x0 squared. Okay, actually we also have an m omega divided by h bar in here. We can also use 1 divided by x0 is equal to square root of m omega divided by h bar. Okay, so this term becomes 1 divided by square root of 2 x0. The x0 is out of the square root. Okay, the square root of 2 is already here in the denominator. Okay, so this term becomes 1 divided by square root of 2 x0. Okay, and in both terms we have bra x prime ket 0, which is pulled out. And the first term is x prime. The second term is written as minus x0 squared because we have this h bar divided by m omega, which is x0 squared. So this becomes minus x0 squared d by dx prime. Okay, we now have the form of the first excited state wave function, which is 1 divided by square root of 1 factorial, 1 divided by square root of 2x0, and multiplying x prime minus x0 square d by dx prime, and all this acting on bra x prime ket 0. We already know bra x prime ket 0, which is the ground state wave function we just wrote down. Substituting that in here gives us the first excited state wave function. Okay, We now have the first excited state wave function in terms of the ground state wave function. And the ground state wave function we had already found out. We can just substitute this in here to find the first excited state wave function. Let's make the substitution. On this side, we collect all the constants. This is the constant, the normalization constant of the ground state wave function, which is 1 divided by pi raised to 1 by 4 square root of x0. Okay, and here we have certain constants, 1 divided by square root of 1 factorial, 1 divided by square root of 2 x0. All right, and then we have this x prime minus x0 squared d by dx prime, which is here. Okay, there's a prime missing. And on the right side of this, we have exponential minus half x prime divided by x0 squared. We see that there's an x0 here and a square root of x0. So together we can write this as 1 divided by x0 raised to 1 plus half. Okay. And the rest of the terms here include 1 divided by pi raised to 1 by 4. And this term, square root of 1 factorial multiplied by square root of 2, we can write as square root of 2 multiplied by 1 factorial. And that gives us the first excited state wave function. Okay. Similarly, the wave function for the second excited state is bra x prime ket 2. Again, we can write ket 2 is equal to a dagger squared divided by square root of 2 factorial acting on ket 0. We can pull out this 1 divided by square root of 2 factorial and substitute for a dagger, where a dagger is square root of m omega divided by 2 h bar x minus ip divided by m omega. So this is now the expression for the wave function representing the second excited state. Now the square root of m omega divided by 2 h bar squared can be pulled out, and outside we will have 1 divided by square root of 2 factorial m omega divided by 2 h bar. Okay, what is left is bra x prime x minus ip divided by m omega squared acting on ket 0. Here we have got an operator squared acting on ket 0 in the position representation, all right, because this operator squared acting on ket 0 gives another ket, and if you project it onto x prime, if you project it onto ket x prime, you get the corresponding position representation. Okay, we are now familiar with the logic. This can be written as the position representation of this operator acting on the wave function bra x prime ket 0. So we just have to write the position representation for this operator. Okay, and we already know the position representation for x minus ip divided by m omega. This is something we already found. The position representation for this operator is x prime minus x0 square d by dx prime. Okay, but we have a square of this operator, so we'll have a square here also. All right, so this is the position representation of this operator, and this expression can be written as this position representation of this operator acting on the wave function bra x prime ket 0. Okay, so we get this expression for bra x prime ket 2, or the second excited state wave function. All right, here it's a prime. Okay, now again we have to substitute for bra x prime ket 0, which is the ground state wave function. Just as before, we collect the constants in here. We just write this 1 by 2 here, all right, as 1 by square root of 2 squared. All right, the rest of it is straightforward. Here we have got an x0 squared. In the wave function, the Gaussian wave function, we have got 1 by x0 raised to 1 by 2. So together it becomes x0 raised to 2 plus half. Pi raised to 1 by 4 here also comes from the normalization constant for the ground state wave function. All right, the rest of it is same, x prime minus x0 square d by dx prime, this whole thing squared, acting on exponential minus half x prime divided by x0 squared. Okay, so this gives us the wave function representing the second excited state. I hope that the steps are clear. All right, now if you are not convinced with this particular step, you can easily check that. All right, we know how to check this. Right, so what we need is, I'll just tell you how to check and you can do it as an exercise. All right, what we need to find is bra x prime x minus ip divided by m omega squared acting on ket 0, which can be written as bra x prime x minus ip by m omega multiplying x minus ip divided by m omega acting on ket 0. Now you know what to do. You introduce an identity operator in here in terms of the eigenkets of the position operator. We can write it like this. Okay, integral dx prime ket x, integral dx double prime ket x double prime bra x double prime. We introduce this identity in here. And then we can use what we already know about the position representation of this operator. We can also use the orthonormality condition, bra x prime ket x double prime. There will be terms like this. This can be written as delta of x prime minus x double prime. You can integrate over x double prime and then see that after a few steps, you are going to get exactly this thing. All right. So I leave that part as an exercise for you to practice. Okay. We have found the position space wave functions representing the first excited state and the second excited state. Looking at this, we can write down a general expression for the position space wave function representing the nth excited state. Okay, it's easy to do. Let's look at the first term in the first excited state, in the wave function representing the first excited state. Okay, the term in the first bracket here is 1 divided by pi raised to 1 by 4 square root of 2 multiplying 1 factorial. We can write this as square root of 2 raised to 1 multiplying 1 factorial. Okay. And in the wave function for the second excited state, we have a similar term, but inside this square root we have 2 square multiplying 2 factorial. So in the first excited state we have 2 raised to 1 multiplying 1 factorial, and for the second excited state we have 2 raised to 2 multiplying 2 factorial. So naturally, for the nth excited state, the corresponding term would be square root of 2 raised to n multiplying n factorial. Correct? So if you put n equal to 2, you get the corresponding term for the second excited state wave function. If you put n equal to 1, you get this. All right. Now let's look at the next term. Here we have got 1 divided by x0 raised to the power of 1 plus half. This is for the first excited state. Okay. For the second excited state, we have a similar term, but for the second excited state, the term appearing here is x0 raised to 2 plus half. All right. So for the third excited state, we would expect x0 raised to 3 plus half, or in general for the nth excited state, the term would be 1 divided by x0 raised to n plus half. All right. Again, for the first excited state, here we have this operator raised to the power of 1. And for the second excited state, we have the same operator squared. For the third excited state, we would have the same operator cubed. For the nth excited state, we would have x prime minus x0 square d by dx prime whole raised to the power of n. Okay. And the last term appearing here is the same in all the wave functions. And we know that this comes from the ground state wave function. What we have done is, starting from the ground state wave function, we obtained the wave functions representing the excited states also. And we have done this by successively applying the creation operator, a dagger, to the ground state. Okay. Let's now move on to the calculation of expectation values and uncertainties. We shall start by looking at the expectation values of x and p. The expectation value for x in an energy eigenstate ket n can be written as expectation value of x in an energy eigenstate is bra n x ket n. This can be easily calculated by using the expression for x in terms of creation and annihilation operators. So we can write this as bra n square root of h bar divided by 2 m omega a plus a dagger acting on ket n. The square root of h bar by 2 m omega can be pulled out, and then we have bra n a ket n plus bra n a dagger ket n. Okay, now we can use the relation a acting on ket n is equal to square root of n multiplying ket n minus 1. So this becomes square root of h bar divided by 2 m omega bra n square root of n ket n minus 1 plus, again here, a dagger acting on ket n gives square root of n plus 1 multiplying ket n plus 1. Okay, and we have bra n square root of n plus 1 multiplying ket n plus 1. Okay. This number can be pulled out, and then we are left with bra n ket n minus 1, which is 0, because these are orthogonal eigenkets of the Hamiltonian. Okay, or the orthogonal eigenkets of the number operator. So this is 0. All right. Here also the square root of n plus 1 can be pulled out, and we have bra n ket n plus 1. This is also 0 because these are orthogonal states. Okay. Same kind of calculation or similar calculation will show that the expectation value of P is also 0 in an energy eigenket, in any energy eigenket. Okay, so we have the result. The expectation values of X and P are 0 in any energy eigenket. Okay, let's now calculate the expectation values of X square and P square for the ground state. For this, again, we can start with X equal to square root of H bar divided by 2 m omega A plus A dagger. Then X square is H bar divided by 2 m omega multiplied by A plus A dagger squared, which is A plus A dagger multiplying A plus A dagger. Okay, this is H bar divided by 2 m omega. Let's carry out this multiplication. All right, we have A multiplying A, which is A square, and then we have got A multiplying A dagger, which is A dagger. The next term is A dagger multiplying A, so plus A dagger A, and then the last term is A dagger multiplying A dagger, which is A dagger squared. Okay, remember that when we have this kind of an expression, you should not simply use the A plus B whole square formula, because A and A dagger do not commute. A dagger is not equal to A dagger A. Okay, so you have to write these terms separately. So we have X square is equal to H bar divided by 2 m omega A square plus A dagger square plus A dagger A plus A dagger. We can now calculate the expectation value for X square in the ground state. Okay, the expectation value of X square in the ground state is expectation value for X square in the ground state is bra 0 X square get 0. Now we substitute for X square from here. H bar divided by 2 m omega can be pulled out. So this is H bar divided by 2 m omega. Bra 0 A square plus A dagger square plus A dagger A plus A dagger plus A dagger acting on get 0. Okay. Now let's look at this first term. The first term would give bra 0 A square ket 0. This is equal to 0 because A acting on ket 0 is equal to 0. Alright, this was the definition for the ground state. So this term is going to give a 0 contribution. Alright, and here we have an A dagger A, but A dagger A acting on ket 0 also gives 0 because A acting on ket 0 is 0. Alright, so this term also will give a 0 contribution. Let's look at this term. A dagger square acting on ket 0 will take us to a state ket 2. Okay, because this is the raising operator acting twice on ket 0. But ket 2 is orthogonal to ket 0, so bra 0 ket 2 is going to be 0. For this reason, this term is also going to give a 0 contribution. The only non-zero term we will have is bra 0 A dagger ket 0. Let's calculate this. All right, bra 0 A dagger ket 0. Now we can make use of A dagger acting on ket 0 can be written as square root of n plus 1. So that would be square root of 1, which is 1. Okay, multiplying ket 1, because A dagger acting on ket n is square root of n plus 1 multiplying ket n plus 1. All right. Now this A, we have got bra 0 A ket 1, but A acting on ket 1, we can use this relation. A acting on ket n is equal to square root of n ket n minus 1. Okay, so this simply gives bra 0 ket 0, which is 1, because these are the orthogonal or orthonormal eigenkets of the Hamiltonian operator. Okay, so the contribution from bra 0 A dagger ket 0 is just 1, which means that the expectation value for X square in the ground state is now H bar divided by 2 m omega. Okay, the expectation value of X square in the ground state we found to be H bar divided by 2 m omega, but this H bar divided by m omega was already defined as x0 squared. So the expectation value of X square in the ground state can now be written as x0 squared divided by 2. Okay. In the same way, we can calculate the expectation value for P square in the ground state. We just start with the expression P is equal to I square root of m H bar omega divided by 2 minus A plus A dagger. Okay, you can now find the square of the P operator just as before. All right, and the expectation value of P square in the ground state can be calculated as bra 0 P square ket 0. Alright, you substitute for p square in terms of a and a dagger, you get minus m h bar omega divided by 2 bra 0 a square plus a dagger square minus a dagger minus a dagger a acting on ket 0. Okay, this is just p square. Alright, now again the contribution from this term is going to be 0 because a acting on ket 0 is 0. The contribution from this term is also going to be 0 because a dagger square will take this to a state ket 2. Okay, and bra 0 ket 2 is 0 by orthogonality. So this is also 0. Alright. Similarly, so this contribution is also 0. Similarly, the contribution from this term is also 0 because there's an a acting on ket 0 which is 0. Alright, this was the definition for the ground state. The only non-zero contribution now is from this term minus a dagger. Alright, minus can be pulled out and cancelled with this minus here. So we have mh bar divided by mh bar omega divided by 2 multiplying bra 0 a dagger ket 0. Now again we can use a dagger acting on ket 0 is equal to square root of 1 multiplying ket 1 which is ket 1. Alright, so this becomes mh bar omega divided by 2 bra 0 a ket 1. Now a acting on ket 1 is again square root of 1 multiplying ket 0 which is ket 0. So this is mh bar omega divided by 2 bra 0 ket 0, and bra 0 ket 0 is 1 because these are orthonormal eigenkets. Okay, and finally we have the expectation value for p square in the ground state to be mh bar omega divided by 2. Okay, let's now calculate the expectation value of the Hamiltonian in the ground state. And the Hamiltonian is p square divided by 2m plus half m omega square x square. This is the kinetic energy operator and this is the potential energy operator. So the expectation value in the ground state is written as the expectation value of the kinetic energy operator in the ground state plus the expectation value of the potential energy operator in the ground state. Okay, the 1 by 2m can be pulled out, so we have 1 divided by 2m expectation value of p square plus half m omega square expectation value of x square. We have already calculated the expectation value of p square in the ground state, which was mh bar omega divided by 2. We had also calculated the expectation value of x square in the ground state, which was found to be h bar divided by 2m omega. Okay, here we see that the m cancels and the expectation value of the kinetic energy is h bar omega divided by 4. Here the omega cancels, m also cancels, and the expectation value of the potential energy is also h bar omega divided by 4. Adding this, we get the expectation value of the Hamiltonian in the ground state, which is equal to h bar omega divided by 2. Now, if you wanted just to calculate the expectation value of the Hamiltonian in its own ground state, we did not have to do all these steps because we are calculating expectation value of the Hamiltonian in its own eigen state. Here we can use the eigenvalue equation h acting on ket n is equal to n plus half h bar omega multiplying ket n, which means that h acting on ket 0 is equal to half h bar omega multiplying ket 0. We can substitute this in here and the expectation value of the Hamiltonian would become bra 0 half h bar omega ket 0. Okay, and the half h bar omega can be pulled out. Bra 0 ket 0 is 1 because these are the normalized eigenkets of the Hamiltonian. So you simply get half h bar omega, which is the same as this. Now this is a general result. If you try to find the expectation value of an operator in its own eigenket, okay, you are going to get the corresponding eigenvalue. So the expectation value of the Hamiltonian in the ground state is simply the ground state energy, which is half h bar omega. Okay. We note that the expectation value of the kinetic energy is h bar omega divided by 4, which is half the expectation value of the Hamiltonian. And the expectation value of the potential energy is also h bar omega divided by 4, which is again half of the expectation value of the Hamiltonian in the ground state. Okay. Let's now calculate the dispersions of position and momentum in the ground state. The dispersion of the position operator, which is written as expectation value of delta x square, can be calculated as expectation value of x squared minus square of the expectation value of x. But expectation value of x itself is 0 for the ground state, so this term is 0. and the expectation value for x square we had already calculated. It is h bar divided by 2m omega. Similarly, the expectation value for delta p square can be written as the expectation value of p square minus the expectation value of p squared, okay, or minus the square of the expectation value of p. Again, the expectation value of p is 0, and we get expectation value of p square, which is equal to h bar m omega divided by 2, as we had already calculated. Okay. So these are now the dispersions of the position and momentum operators in the ground state. So the dispersion of position in the ground state is h bar divided by 2 m omega, and the dispersion of momentum in the ground state is h bar m omega divided by 2. The product of these uncertainties now become expectation value of delta x square multiplied by expectation value of delta p squared. This is equal to h bar divided by 2 m omega multiplying h bar m omega divided by 2. You see that this product is, or the product of uncertainties in position and momentum corresponding to the ground state is h bar square divided by 4. The product of uncertainties is equal to h bar square divided by 4. Now we have seen earlier that the generalized uncertainty relation says that the product of these uncertainties, okay, expectation value of delta x square multiplied by expectation value of delta p square, this has to be greater than or equal to h bar square divided by 4. Okay, so here the equality is satisfied, which means that this state corresponds to a minimum uncertainty state for the position and momentum. In other words, the ground state of the harmonic oscillator is a minimum uncertainty state. This is not surprising because we had the ground state wave function bra x prime ket 0 is equal to 1 divided by pi raised to 1 by 4 square root of x0 exponential minus half x prime divided by x0 squared. Okay, and this wave function is a Gaussian. The ground state wave function of the harmonic oscillator is a Gaussian wave function. Okay, and when we discussed Gaussian wave packets, we had already shown that it represents a minimum uncertainty state. Okay, but if you calculate the uncertainty products for the excited states, you will find that these are going to be larger. It can be shown that delta x square expectation value multiplied by delta p square expectation value is equal to n plus half whole squared multiplying h bar squared. This is for a general state ket n. Clearly, this is greater than h bar square divided by 4 for n not equal to 0. Right? If n equal to 0, this is equal to h bar square divided by 4, which is the minimum uncertainty product. But if n is not 0, you see that this is greater than h bar square divided by 4. Now we haven't carried out this calculation, and I leave it as an exercise for you to calculate this thing, right? The product of uncertainties for a state ket n. This is easy because the expectation value for x and p for any state, any energy eigenstate was shown to be 0. Alright, so you only need to find the expectation value of x square and the expectation value for p square. Alright, now this can be easily calculated by using or by writing x square in terms of the creation and annihilation operator here and p square in terms of the creation and annihilation operator in here. And then you can use the relation a acting on ket n is equal to square root of n multiplying ket n minus 1 and a dagger acting on ket n is equal to square root of n plus 1 multiplying ket n plus 1. Using this and the orthonormality relations, you can find the expectation value for x square and p square for any energy eigenket denoted by ket n. Once you have this, once you have the expectation value, once you have the expression for expectation value of x square and the expectation value of p square, you can find the dispersions. All right, because the dispersion is given as delta x square expectation value is equal to expectation value of x square minus square of the expectation value of x, and this is 0. All right, so this dispersion in position is simply the expectation value of the square. All right, it's the expectation value of x square, which we calculated here. Similarly, the expectation value of delta p square, okay, this is equal to the expectation value of p square itself. So please carry out this calculation, and it will give you some practice in working with the creation and annihilation operators. If you have any difficulty in the calculation, please let me know. Let me conclude with that. I hope you were able to follow the class. Thank you.